Okay, you've just turned in homework number 2, and homework 3 is posted on Blackboard now. We'll be going through an example in today's class that would allow you to get started on homework 3 if you want to get an early start. It's not due till Wednesday of next week, but you'll be able to make pretty good progress on it after today. Today we're going to really quickly just talk about how to handle head loss calculations when you have a non-circular pipe. And then we'll move into this Three Reservoirs problem, and that is the problem that has the Excel template on Blackboard that I mentioned just a minute ago. Does anybody have any schedule or announcement related questions? All right. Sometimes pipes aren't circular, and when they are, there's a number of simplifications that we can apply. Most notably, remember that hydraulic radius is just the diameter divided by 4 when you've got a circular pipe. So when you have a non-circular pipe, any equation that we've been using that has a D in the equation, we're going to have to find some substitution for that. For example, the Darcy-Weisbach equation, pretty soon you're going to be able to write it from memory. Let's see if I can. H sub f equals FLV squared divided by D2G. Okay, good. I never know if I've somehow forgotten it, or it's like sometimes you're standing at the front of the classroom, you forget things. But D means diameter, circular. That's a property of a circular pipe. What if you have water flowing through a rectangular, square, or arched pipe that isn't circular shaped, and you want to use the Darcy-Weisbach equation? You don't have a diameter anymore. So what's the replacement for that? If we can't use diameter, then the simplification is actually pretty simple. It's just, think about, as an illustration, how we calculated hydraulic radius. It was the area divided by the wetted perimeter. So if we don't have a diameter, what we can do instead is substitute in 4 times the hydraulic radius in place of the diameter. And that'll work. That'll give us what we need. And all the other formulas that rely on D work out the same way. In the case of Reynolds number, where it's velocity times diameter divided by the kinematic viscosity, instead of diameter, we say 4 times the hydraulic radius. And so that is going to work for us regardless of the pipe shape, because if it's an arch shape, we could do some sort of a numerical integration, like if we have to, because it's a really complicated arch shape that we couldn't necessarily calculate the area or wetted perimeter directly. We could calculate it numerically and then substitute in 4 times the hydraulic radius and determine the Reynolds number. Relative roughness. That is the vertical axis on the Moody diagram. Remember, the Moody diagram has on the horizontal axis the Reynolds number. The vertical axis has relative roughness. And so that's talking about the equivalent sand roughness relative to, normally we'd say diameter. So normally the relative roughness is K sub S to D. Well, if you have a non-circular pipe, as you'd suspect, we just substitute in 4 times the hydraulic radius instead of diameter. So now that you know, it's easy enough to see how this would fit together. For example, if we had water going through a box culvert. Because we're trying to save some time for the Three Reservoirs problem, I won't ask you to calculate this one. Let me just show you the calculations, and we'll save a bit of time that way. But the setup is we have water flowing through this concrete culvert, and the fact that it's concrete is what specifies the equivalent sand roughness of 1.6 millimeters. Its shape is 1.25 meters by 1.25 meters, and then it has some length, not specified, but we don't need to know it in this case. Oh, actually, we would need to know it. Does it say what the length is? 12 meters long. Okay, there it is, right in the problem statement. So to start things off, remember the F value requires us to take into account not only the relative roughness, but also the flow conditions. And for us to know the flow conditions, we have to be able to say what's the Reynolds number. So the calculations here are that we would start by determining the hydraulic radius. So hydraulic radius for a rectangle, the area is just 1.25 times 1.25. So the area is 1.56 meters squared. You can see the wetted perimeter means what is the perimeter that water will be in contact with when the pipe is flowing full. So that would be 4 times the length of 1.25 meters, because it'll be touching, when it's flowing full, water will be in contact with both of the sides, the bottom, and the top. So the perimeter that we're talking about is this perimeter around the outside. And so relative to the area, the hydraulic radius is 0.3125. And so 4 times this is what we'll use as the substitute for the diameter in all of our equations. So here I've calculated the Reynolds number. I must have been feeling a little bit contrarian because I used the absolute viscosity and the density rather than my normal approach of kinematic viscosity. By the way, kinematic viscosity is just the absolute viscosity divided by the density. So if you've forgotten that relationship from fluid mechanics, that's, if we know the fluid's density and the fluid's absolute viscosity, we can calculate the kinematic viscosity directly. Here, we were given the absolute viscosity. We know that water's density is 1,000. So long story short, we substitute in this 4 times the hydraulic radius where we normally would have the diameter and calculate the Reynolds number. And then it's with the Reynolds number and the relative roughness, we can calculate the F value with the Jane equation. So remember, Jane equation usually is, in this first term, it is the equivalent sand roughness divided by 3.7 times the diameter. This time, instead of divided by 3.7 times the diameter, it's divided by 3.7 times the 4 times the hydraulic radius. So it's this substitution here, 4 times hydraulic radius, also goes into the Jane equation in place of diameter. So we get the F value, kind of a middle of the range F value, 0.022, and then substitute that into the Darcy-Weisbach equation. Water's flowing pretty slowly through this culvert, and that's why we have such a minimal head loss, is when you've got a velocity of less than 1 meter per second and a relatively large cross-sectional area, then you're not going to have a lot of energy loss through that culvert. But that gives you a sense for how to handle it when you have a non-circular conduit. It's just finding what we think of as an equivalent diameter. Like if that rectangular shape was being expressed as a diameter, what diameter would it be? It would be the diameter that is 4 times the hydraulic radius. So any questions about that substitution? All right. Now with that behind us, we can move on to the real meat of today and Friday's class meeting, and that is the Three Reservoir Problem. Now, I really love this. There's just certain problems that are like intellectually stimulating, and this is one of them. But it's not just about this particular problem. It's like what I like about this is it teaches us tools and a thought process that you can apply to other problems as well. So it's interesting hydraulically, but it's also interesting because it'll allow us to sharpen our logic and problem-solving skills. And so don't think of this as just like a hydraulic engineering problem. It is, but it's a hydraulic engineering problem that you're going to learn kind of a mindset that you could apply to other problems in structural analysis, mechanics. There's other applications to these same kind of problem-solving methods that we're going to apply. So with that said, is the preamble that it's more than just about hydraulics here. Let's say that we've got 3 reservoirs connected together. And the high, middle, and low is talking about the elevation of the water. And they're connected at a single junction. So reservoir B is the one that's way high up on the hill. Reservoir C is at the bottom of the hill. And reservoir A is somewhere in the middle. Now, when you have a situation like this and it's connected by a central junction, the question is, what way is the water going to be flowing? We've learned before that water flows downhill, and it still does here. And so water's going to be flowing from the high reservoir, like outward, out of the high reservoir, because that's where there's the most energy. And water flows from high energy to low energy. And so for that same reason, the water's going to be flowing in to reservoir C. Okay, so far so good. But the thing that's indeterminate, that we don't know just at a glance, we're not sure whether the water is going to flow in or out of reservoir A. So let me ask you, what if reservoir A was almost as high as reservoir B? Like it was like an inch lower for the water surface. Then what would be your guess? Is the water going to flow in to reservoir A or out of reservoir A if it's almost as high as reservoir B? Out. Good. Good guess. You've got good instincts. Reservoir A, what if it's almost as low as reservoir C? Then is the water going to flow in it or out? In. Okay. So it partly depends on the water surface elevation of this metal reservoir. But really the way that we're going to look at it is both what is the elevation of that water surface, but also the most important thing is how much energy is there at D. Because remember, water flows downhill. It flows from high energy to low energy. And so we don't know really if the water is going to go in or out of A until we know, is there more energy at D than A? And if there is, if there's more head, we're going to measure the energy in units of length. So measuring energy in units of length, that's head. So if there's more head at D, then the water will flow from D to A because it goes from high energy to low energy. Or if the elevation of A is higher than the head at D, then that's going to push the water from A towards D. So this analysis, the problem we're trying to solve is not only what direction is the water going through each of these pipes, but also what's the flow rate, like how much water is going through each of the pipes. And then if we know how much water is going through each of them, then that could allow us to calculate, for example, the pressure distribution in the pipe. So we could find out like what's the pressure at junction D, which may be important if we've got a valve there or if it's a welded fitting and we want to check how does the pressure compare to what the welds are rated for. There's a number of reasons why maybe we're interested in the pressure. But once we answer what is the flow rate, then we can calculate everything else. So that's the main question, is what direction is the water flowing and how much? And then part of that is the pressure at the junction. So the approach here is that we know water flows out of the highest reservoir into the lowest reservoir, but we're not sure about the middle reservoir at first. So since we're not sure, we have to start with a guess. And then we're going to check our guess. And starting with a guess will just kind of allow you to get started with the calculations. You can kick things off. For example, if we're having to calculate energy loss through the pipe, we don't know what is the energy loss through the pipe until we know what the flow rate is. But we don't know what the flow rate is until we know the energy loss through the pipe. We've been through this before, right? Where we don't know something until we know the other thing, but we can't know the other thing until we know the first thing. And so the way we got around that before was just by starting with a guess, checking the guess, correcting, making a little bit better than our initial guess until eventually we have convergence. So we're going to do the same thing here. The flow rate through each of the pipe depends on the energy difference between the reservoir and the junction point. And we'll define head loss as being the difference in energy from one point to the other. And once we know head loss, so H sub F is head loss, then we'll use the head loss to calculate S sub F. And does anybody remember what's the name of this variable S sub F? That's right, the friction slope or the slope of the energy grade line. So we'll need that slope of the energy grade line to tell us what is the velocity through the pipe. Today we're going to be, because the three reservoir part of it's hard enough, we'll use a simple method for calculating energy loss. So remember, the simple method for calculating energy loss is the Hazen-Williams equation. And then on Friday, once we have a handle on the three reservoirs part of it, then we'll start using Darcy-Weisbach as our method for estimating the relationship between head loss and flow rate. But for today, we'll use this easy approach. What makes this approach easy, by the way? Anybody remember why is the Hazen-Williams equation the easy one?
Is it because of the Reynolds number?
Kind of. That's part of it, yeah.
Wasn't it do with the CH value?
Yeah, what about, you're right. What about the CH value?
Wasn't it like a given value or something like that?
Exactly. It's a given. It's a constant. It doesn't change with Reynolds number. So Darcy-Weisbach is complicated because the F value is sensitive to changes in diameter or flow rate. But what makes this easy is we just look up the C sub H based on what kind of pipe material we've got, and then we're not having to constantly fiddle around with it and change it when the flow conditions change. So that's why we're going to use this one, just so that for today we can focus on the three reservoirs part of it and not get hung up on perfecting our roughness coefficient. Okay, so this is the problem we're going to look at. And that template file that I mentioned is available on Excel. If you've got your laptop today, please get it out. If you don't have a laptop today, bring one on Friday, because it's okay maybe just to watch what we're doing for this one, but you should get some hands-on experience in the classroom. So bring your laptop on Friday if you don't have it. Well, bring it regardless of whether you have it today. If you do have your laptop today, also bring it on Friday. Okay, so we put some real numbers into this one. We've got 85 feet is the elevation of the highest reservoir. We're going to call that reservoir P. So by inspection, we can see that the water's flowing out of P and towards R, R being that common junction. The lower reservoir, T, has a water surface elevation of 15 feet. And so by inspection, we can tell that the water is going to be entering that reservoir. We don't know the flow rate yet, but we do know the flow direction. And we know the elevation, the physical elevation of junction R. So it says down here at the bottom that Z sub R is 35 feet. So that's just kind of its physical altitude. And we don't need to know its physical altitude to determine like the flow rates, but we do need to know it to calculate the pressure, which is going to be the last thing that we do. So the elevation of that junction is not a necessary piece of information to solve the three reservoir flow rate issue, but it is to know what's the pressure. So here's the method that is implied in this spreadsheet. Now I put the spreadsheet template together myself. There's nothing magical about it. It's not from the textbook manufacturer. It's not like a standard method ASTM thing. So, I mean, there's nothing sacred or holy about it. You can make your own template file. I just put it together based on the steps that I like to go through, the notations that I think make sense. And so feel free to start with a blank workbook if you prefer it that way. But I think it gives us good guardrails for the first time you're solving the three reservoirs problem. So the method that's implied by that spreadsheet is that we're going to start with a guess for the head at the junction. So that is how much energy is there at R. And then once I know how much head there is, then it'll tell me whether the water's flowing in to M or out of M. So for example, if I said H sub R is 21, so if I said the total energy at R is 21 feet, then is the water going into M or out of M? Because M is at an altitude of 20, the water surface is. So if there's 21 feet of head at R, then what direction is the water flowing? Don't be shy.
Into the reservoir.
Into the reservoir, yeah. Because if there's more head at R, it pushes the water from R towards M. Do you have a question?
Yeah, is that so? I mean, doesn't it matter like where the pipes connected to the reservoir?
It's that the amount of head there is independent of its elevation. So it's an interesting thing that, like, what is head? When we're talking about head, that's the energy that is in the pipe, and it is the sum of three things. There's three things that give water energy. So the head at location R is Z sub R plus VR squared divided by 2G plus the pressure at R divided by gamma. So the energy comes from the elevation, the velocity, and the pressure. So if I say that the head at R, if I say it's 21 feet, then if the physical altitude is 35, then that would mean most likely that we have a pressure that's below atmospheric pressure. So like there's suction in there. Now there's a limit to how much suction you can have because you can't go less than 1 atmosphere before the water begins to cavitate. But yeah, so when we're making a guess for how much head there is at R, sometimes a good starting point would be just, well, you could say let's say that the head is just only the physical elevation. Then what would the flow directions be? What would be the flow rate? Our textbook suggests that maybe for your first iteration, you could assume that the head at R is equal to the elevation at M. I don't like that approach though, because then you don't have any flow through this pipe MR. So I'm going to suggest for our first iteration, we'll do a guess of 50. So let's look at that. Let's open up this this spreadsheet template. And by the way, there's this warning here that I want to highlight before we actually start the calculations. So if you say that the head at R is 21, then the water's flowing from R to M. If you say it's 19, then the water's going to go from M to R. So if you change, like if you make the head above and then you're going from below, you have to be careful in the spreadsheet because then continuity is going to be a different formula. So just as a setup here, if the head at R is 21, if H sub R is 21 feet, then that means that QPR, and if it's 21, then the water's going into M, is equal to QRM plus QRT. So if the water's going into M and into T, then the flow rate through this pipe is equal to the flow rate through those other two. Continuity principle. The flow in to the junction is equal to the flow out of the junction. So if a liter of water comes into R, that same liter of water has to be split between the other two pipes. So that would be, this is our continuity relationship if the water is going into junction M. But what if the head was 19 feet? This equation no longer applies if the head is 19, because now if it's 19 feet, then the water's going from M towards R. So now it would be that QPR plus QRM is equal to QRT. So that's the warning here. Sometimes there's going to be like the continuity relationship, that formula that says the flow in equals the flow out. You have to be careful if you've crossed that threshold of the head at R is equal to the head at M. All right. So here's our template file. It's the same figure. We've got the plastic pipe with a given C value, cast iron pipe with a given C value. We know the diameters, the lengths, galvanized iron. So we've got 3 different pipe materials, 3 different diameters, 3 different lengths, trying to intentionally make it dissimilar just so we can get some experience setting up the calculations. Okay, so the lines that we have, there's line P dash R. There's going to be line M dash R, and there's line T dash R. So those are the pipes that we've got. We just name them in the direction of, like, the junction name first, and then the reservoir name, and then the junction. Okay, PR is plastic. MR is cast iron. And TR is galvanized iron. Okay, and the C values are given for each of those. For the plastic, that's 150. Cast iron is 130. And galvanized iron is 120. Let me zoom in a little bit just to make sure that that's a little bit easier to see. Can you see that in the back row? Yeah? Okay, good. This initial stuff is, we're not doing problem solving yet. We're just transcribing the problem statement into the template. So 600 length for PR, 1300 is the length for MR, and 1350 is the length for TR. Diameter, we need to have the diameter in feet. So we can say that pipe PR is 12 divided by 12, 1 foot diameter. MR is 6-inch pipe, so 6 divided by 12. And then TR is an 8-inch pipe, so equals 8 divided by 12. So we've got our diameters. Cross-sectional area is pi d squared divided by 4. So equals pi, open close parentheses, times the diameter squared divided by 4. Okay, so we've got the areas of the pipe. Now, our initial guess, let's just say, what if there's 50 feet of energy at R? Let's use that as a starting guess. So 50 feet. And rather than type 50 in 3 times, I'm just going to have equals and refer back up to here. Equals, refer to the cell above it. Okay, so that way if I wanted to change my guess, everything updates automatically based on the value I have in the first cell. All right. Now, if there is 50 feet of head at the junction, then what is the head loss through pipe PR? So P is 85 feet is the reservoir elevation. And so that's the Z. That's the elevation of the water in the tank. There's no velocity for the water in the tank. It's quiescent water that's not moving anywhere. It's just at the surface of a tank. So we can say there's no velocity head, and we can see the little triangle and the ripple marks. That tells us it's open to the atmosphere. So there's no pressure at the top of the tank. So the water surface elevation is where all of the head comes from at P. So the head loss through the pipe is 85 minus 50. So it's the water elevation of 85 minus whatever the guess of the head is at that location. So it'll be, if the head at junction R is 50, then that by definition means that there's 35 feet of head lost through the pipe. Likewise, if the head is 50 at R, then the head loss from 50 to 20, we have to set that up as 50 minus the given elevation of 20 feet. So it would be 30 feet of head loss. And then if it's 50 at R, it's going from 50 to 15. So it's going 50 minus 15. So look, sometimes I type in the elevation first, and sometimes it's referencing the head guess at R first. It depends on the implied flow direction by what head that you've guessed. So if you look at the formulas, I did 85 minus the guess for that first pipe, but then it's the guess value minus 20 for the second pipe and the guess value minus 15 for the other one. So you have to know, is the guess head above or below the water surface? And then that tells you how to calculate the H sub F. The H sub F should never be negative. Head loss is always a positive quantity. How much energy is lost as the water's flowing through the pipe, that's always a positive quantity. Okay, slope of the energy grade line. We learned from this other slide that slope of the energy grade line is H sub F divided by L. Okay, so it is this H sub F divided by the length of the pipe. Now remember, we can apply that down. This isn't definitely the slope of the energy grade line. This is the slope of the energy grade line if, it's the slope of the energy grade line if there was 50 feet of head at R. We don't know how much head there is at R. We can correct the guess later on, but we'll just start by saying, like, if it was 50, then all of this stuff follows. And what we know has to be true is we know that the flow into the junction has to equal the flow out of the junction. And if that ends up not being true, then that tells us we need to make an adjustment to our guess of how much energy there is at R. And so that's what we're going to use as the guiding principle is, does flow in equal flow out? If not, make a change. And if so, that could be an indicator that the solution has converged and that you've got the correct value for the head at R. Okay, so this is a guess, and all of these other calculations are just what if the guess is true? Or, like, what would be the value based on that guess? Okay, so if this is the slope of the energy grade line, now we can use the Darcy-Weisbach, this is the Hazen-Williams equation. We can use the Hazen-Williams equation to calculate the velocity. All right, so let's do that. Velocity equals 1.318 times the C value times hydraulic radius. That's not one of my columns. I don't have hydraulic radius. Anybody remember what's the hydraulic radius of a circular pipe when it's flowing full?
Would it be the area?
D over 4. Yeah, diameter divided by 4. So what I'm going to do here is have parentheses, and it's D divided by 4. That's the hydraulic radius for a circular pipe that's flowing full. I could have added a column that is called hydraulic radius, rather than embedding that calculation into this equation. But I forgot to do that. Okay, so hydraulic radius to the power of 0.63 times the slope of the energy grade line, which now, since my equation is centered, it's on top of the cell that I want to click on. So I can't click on the cell, I have to type it in. It's I-27. So slope of the energy grade line to the power of 0.54. Okay, so now I've got my equation for the velocity. So that tells me if the head at R is 50, then the head loss is 35. If the head loss is 35, then the slope of the energy grade line is 0.058. If that's the slope of the energy grade line, and based on the material, based on the diameter, then the water would be flowing 17.8 feet per second. The flow direction to junction. The water is flowing into the junction from this location. And the flow rate, if this is the velocity, then the flow rate is velocity times area. So V times A gives us Q. Q equals VA. Okay, so all of this contingency is suggesting that we would have a flow of 13.976 cubic feet per second out of the pipe if that was the head at junction R. Okay, now I can drag this formula down to calculate the velocity in the other pipes. It doesn't require any special consideration. It's just going to determine the velocity based on the slope of the energy grade line and the pipe's diameter. Okay, so we've got velocities. But we do need to now think and apply our logic here. Is the water flowing into the junction from that pipe or out of the junction from that pipe? So if the head at R is 50, then that means the water is flowing out of junction R towards M. So it's out, and it's out here. So in from the reservoir towards R, because the elevation there was 85, and the elevation here is, in our guess, just 50 for the head. So we want to be careful about making sure that the in and the out is correctly designated. The flow rates, we can just drag the formula down there because it's going to be the velocity times the area. But now we want to check and see, like, how close is the continuity equation? Does in equal out perfectly, or is there an imbalance? And if there's an imbalance, that tells us how we have to change our guess for how much head there is at the junction. So what this is saying is, in this cell, let's calculate out minus in. So it's the outflows. There's two of them. It's this out plus that out. Those are the outflows minus the inflow. Okay, and then our little thing here is saying if the out is bigger than the in, then the guess of the head at R is too high. Is that true? Is the outflow bigger than the inflow? No, actually it's the reverse of that. There's way too much flow coming in and too little flow going out. So think about what that means. The amount of head at R. Our guess is suggesting that there would be a lot of flow, like if the elevation is that high, then there would be a lot of flow through pipe PR, but very little flow through these. So I think what that means is that we're going to have to adjust our guess of the height, that the guess is too low. So I'm going to write here, since Q in is bigger than Q out, that means our initial guess of the head at R is too low. We need the head at R to be bigger, and if the head at R is bigger, then what that's going to do, it's like we're raising the energy at R. That'll increase the flow through these other two pipes. And then that would decrease the flow through pipe PR. And so it would make it more balanced. Okay, so now we have iteration 2. We can copy all of the constants. Like all of this is just duplicated for this next one. So I'm going to do Control C and then Control V to paste it. Now I want a better guess. So 50 was too low, so let me try 60. 60 and all right. So it's not going to change what is an in and what is an out. So the warning here that we had, where was that warning? This warning, adjusting the elevation of the head is not going to change what we're considering an inflow and an outflow. So the head loss is going to be, through the pipe, it would be 85 minus this. It would be this minus 20. and this minus 15. Same approach for calculating how much head loss there is. It depends on what our guess is. We've raised the guess, so that's reducing the head loss through pipe PR, and the head loss is what's driving the flow rate. So this Q is really big because the slope of the energy grade line was big. So it's too big. What we determined is because in was larger than out, that told us that guess was too high. So we need to bring, or I'm sorry, the guess was too low because the slope of the energy grade line was too high. So if we raise that, getting it closer to the water surface of reservoir P, then that's going to reduce the slope of the energy grade line. So here I don't have to type, well, it's no big deal. Head loss divided by the length of the pipe gives us the slope of the energy grade line. So you can see that now the slope of the energy grade line for pipe PR is lower than it was before, so that's going to reduce the velocity, it's going to reduce the flow rate. These energy grade line slopes are higher, so that's going to give us more flow rate. It's going to bring it so that it's closer to being balanced. So the velocity, I guess I've got the time. Let me get the practice typing in the formula again. Rather than copying, I could just copy and paste, but it's always good to practice the formula. Let me do that. It is equals 1.318 times the C value. This is an error. It should say C. It's just the C value. All right. So back to this formula. 1.318 times the C value times the hydraulic radius. So that's the diameter divided by 4 gives me the hydraulic radius to the power of 0.63 times the slope of the energy grade line to the power of 0.54. Okay, so typed in the Hazen-Williams equation, determined the velocity, drag that down. I won't type it in all 3 times. Again, it's going to be water flowing into the junction from that reservoir and out of the junction from these. Like why in from this one and out for that one? You just have to ask, think about if we're saying that there's a certain amount of head at R. We said in this next guess it was 60. So 60 is below P but above M and T. So the water's flowing from P to the junction and it's flowing from the junction to M and to T. So you just have to kind of either visualize it or think that the flow is into the junction if the pressure at the junction is less than the reservoir elevation. So in, out, out. So flow rate now is velocity times the cross-sectional area. And then we want to look at the consequences of the changes that we made. It brought the flow rate down a little bit for pipe PR, and it increased it a little bit for pipe MR and TR, but is it in balance yet? It's still, I mean, it's obviously, you can see that there's too much flow coming into the junction and not enough flow coming out of the junction. So if we do out minus in, so here's the out minus the in. Okay, it's negative again, so we can say the same thing that we said before. Since flow in is greater than flow out, that means we should raise our guess for the head at R. So what about 61 feet? It's getting better. What about 62 feet? Getting warmer. 63. Okay, now if you know things about Excel, what's a better way than me typing in numbers over and over again? Goal seek. We love goal seek. All right, so what's going to be our target, our objective in the goal seek? We want an error of 0. Say we go to data, what if analysis, goal seek, and our goal is we want this to be 0 by changing the guess head value. Now, this is only going to work if these head values below it dynamically change based on this guess. So that's why I did the relative reference up to that initial guess, is because I want to be able to change one thing and have all of them change. Okay, so set the goal being the error. We want an error of 0, and it can change the guess. So it plays around with that, and it finds that the head that gives us that flow in equals flow out is 79.45. Okay, that's right. We could have done it in the first step, but I wanted to show you moving on. We won't be able to do it all in a single step when we switch over to Darcy-Weisbach, but we can in a single step do that goal seek in the case of Hazen-Williams. Now, what about what's the pressure at R? If these are the flow rates, by the way, does in equal out now? Yeah, in equals out. So that's one indicator of convergence, is that flow in equals flow out. Our C values aren't changing because we're using the Hazen-Williams equation, but that would be the other indicator of convergence. So the pressure at R. Let's calculate the pressure at R. So here are these formulas for how we would calculate the pressure at a location based on the head. So the head at location R, we said, is 70. By the way, this should say R, not D. See, I adapted this from another problem. Okay, so the head at R is 79.5. The elevation in the problem statement said it is 35 feet. So 35 is the given. The velocity head, v squared divided by 2g. We've got 3 different velocities. So I'm going to calculate the average velocity head. So it's the velocity head. So this velocity squared divided by 2 times 9.81. So there's the velocity head there, velocity head in all 3 of the pipes, and then the average velocity head. So I want to find the head, the pressure at this location is the unit weight of water, 62.4 pounds of force per cubic foot, times the head at the junction minus the elevation at the junction minus the average velocity head. And that gives us pounds per cubic foot, pounds per square foot, sorry. And let's see, I think maybe I have an error in my velocity head calculation. Oh yeah, G is not 9.81, not in traditional units, it's 32.2. Come on guys, you got to catch me on these mistakes. 32.2. What was I thinking? Okay, so we got the pressure there, and then in PSI it would be that divided by 144. So there's 18.7 PSI at the junction if the elevation of the junction is that height. All right, it's 11:50, we're out of time. One of your homework problems, if I remember correctly, is a Hazen-Williams version of Three Reservoirs. So you could solve that tonight. You could solve it right now. Just skip your next class, go straight into Three Reservoirs, or whenever you want. You probably want to savor it for later, I bet. Just like candy, wanting to save it for at the end of the day, like as a reward to yourself. So the homework assignment's due on Wednesday of next week. So I'll see you on Friday, and we'll do another one of these Three Reservoir problems.